part 2 of the titration lab, we're specifically going to take a look at a type of titration known as a strong acid, strong base titration. Now, in all titrations of acids and bases, when the acid and base mix together, the products that are going to create upon neutralization is a salt plus water. This will be true for all titrations. Consequently, in an acid-base titration, at the equivalence point, the only things present in a solution are salt and water. This would be because, by definition, when we're at the equivalence point, this would be when the moles of acid and moles of base have completely neutralized each other. Once the acid and base have completely neutralized each other, the acid and base are no longer present, and all that we'd have remaining in the solution at the equivalence point is the salt created by the neutralization reaction and some water. Now, a unique feature of a strong acid and strong base titration is that when we mix a strong acid with a strong base, the salt that they're going to create is a salt that would create a solution that is neutral with a pH of 7. This is unique and specific to the strong acid, strong base titration. For example, hydrochloric acid plus sodium hydroxide is going to create the salt sodium chloride. Sodium chloride is a salt where both ions, the sodium ion and the chloride ions, would be spectators. This would give us a salt solution that's going to be neutral, and we would see at the equivalence point for this particular titration, when the moles of acid and moles of base have completely neutralized each other, at the equivalence point we will see a pH of 7. We have a pH of 7 because the salt that's created here, sodium chloride, is a salt that produces a neutral solution. Another example, if we have, say, nitric acid, we mix it with potassium hydroxide, the salt we get is potassium nitrate. This also, potassium ions would be spectators, nitrate ions would be spectators. This too would give us a salt at the equivalence point that's neutral, so we would see at the equivalence point our solution would have a pH of 7. Now, all acid-base titrations have something that we can produce which is referred to as a titration curve. This is a graph of the titration as it occurs. Now, in titration language, if we say something such as our titration is a strong acid, strong base titration, the strong acid component, what's being titrated, is what's down in the flask. The second thing, when we say strong base, that's the material that's going to be located in the burette that's being added to the flask. This has implications for what our titration curve will look like once it's created. In a titration curve, what gets graphed is the horizontal axis would be, in this case, milliliters NaOH added, because that's what's being dispensed from the burette. And then the vertical axis is the pH of the solution that's in the flask with that's being titrated, in this case, hydrochloric acid. Because hydrochloric acid is a strong acid and dissociates completely in solution, the initial pH for a strong acid is typically going to be fairly low. So for example, let's say we have a pH of 1, and this would be prior to any NaOH being added. The volume of NaOH at this point is 0. We now open the burette, and base starts to drip into the acid solution. The base neutralizes the acid only drop by drop. So as the drops are going in, there's still an excess amount of acid in the flask, which will keep the pH of the solution fairly low as we add sodium hydroxide. So as we progress, we see the pH changing very slightly, if at all, staying fairly low. Because as long as there's an excess amount of the strong acid, HCl, in the solution, it's going to maintain a low pH. We then reach a point where we're within drops of neutralizing the acid. There's only a small amount of excess H plus ions. We add another drop, an H plus ion gets eliminated. The curve starts to go up with a single drop. We add another drop, the next H plus ion is gone, and we add another drop, and now all the acid is gone, and we have in the solution at this point only salt and water. The next drop of base we put in gives us an excess amount of base, so we see the pH readily rising to indicate an excess amount of base. This would now be a titration curve that we would see strong acid, strong base titration. Now, how this curve is used is what we do: go to the vertical break on our graph. We go to about the midpoint of this vertical break, and that's going to represent for us our equivalence point. In a graphical titration, we don't need to use an indicator solution because we can overshoot the equivalence point. We now look at this midpoint, and we see that our pH here is 7, which would be true for a strong acid, strong base titration. And what we can do is take this midpoint and go down, measure on our graph what we would have for our milliliters of NaOH, and that will give us the volume of NaOH that was required to neutralize the acid. This will be another graph representing a strong acid, strong base titration. Again, what we can use here is, because all that's present at the equivalence point is salt and water, in that all the acid has been completely neutralized, and at the equivalence point we do not have any excess base present. We can see right here for the strong acid, strong base titration, we have a pH of 7 at the equivalence point, which would be true for a strong acid, strong base titration. If we extend from this point down, we can see that we reached this point by having added 20 milliliters of NaOH. So graphically, we can get the volume of NaOH that was utilized to neutralize the acid when we use a titration curve. Let's now do a sample calculation for part 2 in the lab. This data could be collected from either using an indicator, where we have the volume of base used to neutralize the acid from a faint pink color that we got, or we may have gotten the volume of the NaOH from using a titration curve. Both means will allow us to solve the problem of figuring out what the concentration is of the HCl. Now, in this part of the lab, we now have a known concentration of NaOH. That's what was determined in part 1 of the lab. Whatever your average concentration was for the NaOH in part 1 of the lab, you now use that as your known concentration for part 2, 3, and 4 in the lab exercise. In this case, we're given that the concentration of the NaOH is 0.10 molar. We can set up a proportion. From the 0.10 molar NaOH, what we know is that we have 0.1 moles of NaOH per 1 liter. Now, the volume of NaOH that we used will let us figure out how many moles of NaOH we used, because if we know we have 0.10 moles of NaOH in 1 liter, we're going to have X moles of NaOH present in the volume of NaOH we used, which is 0.0138 liters. Solving for X, we find that we have 0.00138 moles of NaOH in our sample that was utilized to neutralize the unknown hydrochloric acid solution. Because the NaOH and HCl react in a 1-to-1 ratio, we can say, therefore, we have the same number of moles, or 0.00138 moles of HCl, were present in the HCl sample. Now we have our volume of the HCl that was used, 14.2 milliliters. Concentration is measured in moles per liter. There's two things we need to know. We have to know the moles, which we now know, and we have to know our liters, which is data we collected when we measured out our volume of the HCl solution used. The data we have allows us to set up a proportion. We have 14.2 milliliters of HCl, which we switched to 0.0142 liters, and we know that this volume of HCl contains 0.00138 moles of HCl. So that gives us our numerator. If we know our moles in liters, we can solve for X moles of HCl per 1 liter, and once we have our information in terms of how many moles are present in 1 liter, that would be our concentration of the unknown HCl solution. Solving for X gives us, for this unknown solution of HCl, the concentration is 0.097 molar, or moles per liter.